Hello everybody, my name is Andreas Schmidtner. I'm from Oregon State University and this is my presentation, Glacial Atlantic Meridional Overturning Circulation Strength versus Depth. Most of this work was actually done by Juan Muglia, who used to work with me at OSU but is now at CONICET in Puerto Madryn in Argentina. So it's really his work that I'm presenting here. And I would also like to acknowledge support from the National Science Foundation. So this work is really about the glacial, the Atlantic Meridional Overturning Circulation, or AMOC, during the last glacial maximum 20,000 years ago. And this background figure here shows a calving iceberg from an ice shelf. And these ice-ocean processes, ice-ocean interactions, have perhaps been important in determining the glacial state of the climate system and of the ocean, but they are currently not included in most models, and this has some relevance to this study, so that's why I choose this photograph. Okay, but the motivation really for this study was a previous paper that we published in 2018, shown in the upper right here in EPSL, Earth and Planetary Sciences letters, where we've done a series of model simulations and compared the model results with carbon isotopes from glacial sediments, and we concluded that the best fitting model had a weak and shallow Atlantic Meridional Overturning Circulation, or AMOC, and therefore we concluded that the AMOC during the LGM was weak. But in these experiments, AMOC strength and AMOC depth were correlated, so we could not really distinguish between AMOC depth and AMOC strength, so which of those two properties determines that model fit to the carbon isotope data. So this will be the goal here, to separate those two effects, investigate the effects of AMOC strength and AMOC depth separately, the effects on those carbon isotope distributions and thus on the model data fit to the data, to the sediment data. And the strategy is similar to the previous work. We combine models and data from glacial sediments, model simulations with those data. And in addition to perturbing the southern hemisphere moisture diffusivity in the atmospheric model component, which is a simple energy balance model, this forcing in the southern hemisphere, which essentially controls southern ocean buoyancy fluxes. So, for example, if the moisture diffusivity, the moisture transport in the atmosphere is increased, Antarctic bottom water gets fresher, and that leads then to stronger and deeper AMOC. And so in this forcing results in this correlation between AMOC strength and AMOC depth. So a stronger AMOC is always deeper in these simulations, and a shallower AMOC is weaker. So we combine this now with North Atlantic freshwater fluxes. So we perturb buoyancy fluxes both in the northern and in the southern hemisphere. And this, as we will show, using North Atlantic freshwater fluxes impacts AMOC strength with almost no changes in AMOC depth. So therefore, if we combine these two, we can vary AMOC depth and AMOC strength independently. And the results of this work, if you want to look into the details, are published in the Quaternary Science Reviews paper just published in April this year, 2021. Okay, so here's just a quick description of the model that we use on the left and the sediment data on the right. So let's start with the model. The model we're using is the Oregon State University version of the University of Victoria climate model, OSU UVic. This is a three-dimensional ocean circulation model, a simple one-layer energy balance model, and with that we use the model of ocean biogeochemistry and isotopes, MOBI, which includes full carbon cycle and other nutrient cycles, but important for this work here, it includes also C13, so carbon isotopes, C13 and radiocarbon as well. And it's these two isotope systems that we will compare with the sediment data, so we'll focus on those. So as I mentioned before, in addition to varying the southern ocean buoyancy fluxes as done in the previous study, we now add freshwater fluxes in the North Atlantic to create independent variations of amok depth and amok strength. The sediment data here is just two quick maps from, on the top, the C13 distribution. We use the compilation from Peterson et al. 2014. So this data set has about just over 400 data points, but you can see most of the data are in the Atlantic, with relatively less data in the Pacific and Indian Oceans. And the lower map here shows the radiocarbon compilation by Skinner et al. There we have almost 250 data points and a more even distribution between the Atlantic and the Pacific, although in this case there's almost no data in the Indian Ocean. All right, so those are the data and the model. Now let's move on to the results. Here, excuse me, here is a graph that I'll show you a series of. So let me just try to orient you in what is shown here. So on the horizontal axis we have amok strength, so the maximum Atlantic meridional overturning circulation transport rate at 25 degrees north. And it ranges from about 7 Sverdrup, which would be a very weak amok, to 21, which would be a very strong amok. And then on the vertical axis we have amok depth. So this is determined as the average depth of the zero stream function isoline in the model between 25 south and 25 north. So it ranges from about 1600 meters, which would be a very shallow amok, to about 3200 meters, which would be a very deep amok. Sorry, the units are actually wrong here. This should not be Sverdrup, but meters. And then what is shown here in these different colored dots is the correlation coefficient of these model simulations with the C13 data, with the sediment data. So correlation coefficients in this case range from about 0.65 to 0.8. So these larger numbers for correlation coefficients indicated in these orange, darker orange colors indicate a better fit, whereas the bluish colors indicate a worse fit. So there you can already see, that the deep amok simulations here are blue. They are not in very good agreement with the data, whereas these amok depths of around 2300 meters, they are in these dark orange, so they are in much better agreement with the sediment data. So this is the global here, and let me just orient you a little bit more. So the previous series of experiments that we've done in the 2018 paper is this diagonal here. And there, in this case, you can see amok depth and amok strength was correlated in these simulations, and the best fitting model would be here around 2300 meters amok depth and about 9 Sverdrups amok strength. But from these simulations alone, we could not say, is it amok depth or amok strength that determines the fit to the data. And now that we have filled in this phase space here by adding these simulations, these additional simulations with North Atlantic freshwater fluxes shown here in the horizontal, you can now see that the fit of the data is really mostly determined by amok depth, right? So all of these at a similar amok depth but very different amok strength. These have all very similar values for the correlation coefficient here, and the isolines, some of the isolines are indicated here. They are very horizontal, indicating also that amok strength does not affect the fit to the data very much, whereas amok strength, amok depth shown in the vertical affects the fit with the data a lot. Okay, just for reference, here's the pre-industrial control simulation where that would be situated here. So at the 17 Sverdrups and about 3100 meters. Okay, so this was the correlation coefficient for C13. We can also look at other model data misfit indices, like the root mean squared error shown here now on the right for C13 as well. And now for the root mean squared error, you are looking for blue colors, so low values indicated in dark blue here, indicating a better fit compared with dark orange, which would indicate a worse fit, so larger errors. And again, you can see something similar, very horizontal orientation of the isolines. And in fact, all of these simulations down here below about 2,500 meters AMOC depth are all more or less similarly consistent with the data, whereas here in the upper part, the deep AMOC simulations are not consistent with the data. But in terms of AMOC strength, we cannot really distinguish the results and determine AMOC strength from these results. Another detail I want to mention here, these errors are, the values shown here are normalized by estimated combined model and data errors, which are 0.28 per mil based on modern data. And so what that means is that an RMS error of around 1 or smaller than 1 indicates consistency between model and data. And so you can see all these blue colors here are more or less consistent with the so between model and data. Okay, so those were the global results in these upper panels. Now I added here in the lower panels the Atlantic, and then in the Indo-Pacific and on the bottom. And there you can see, if we just look at the Atlantic first, again for the correlation coefficient, we have very similar results as for the global. This is not very surprising because the C13 data are dominated by Atlantic data, as I mentioned earlier. Most of the data are from the Atlantic. A little bit stronger sensitivity to AMOC depth here, so that perhaps these very shallow AMOC simulations can be excluded from the data. Again, in the for the RMS error, the results are very similar between the Atlantic and the global. And then if we look in the Indo-Pacific down here, we see a little bit more sensitivity to AMOC strength. So these isolines are a little bit more slanted, indicating weaker AMOC strength would be in better agreement with the data, at least for the correlation coefficient. For the root mean squared error, there's not much difference between all of these runs down here in the Indo-Pacific. Okay, so the bottom line is the RMS error and the model data misfit depends mostly on AMOC depth and is not very sensitive to AMOC strength. The global fit is dominated by the Atlantic data, and the Indo-Pacific data seem to indicate slightly weaker favor the weak AMOC simulations. Now for radiocarbon, the results are shown here again. On the left, the correlation coefficient, and on the right, the root mean squared error. Again, you can see very horizontal isolines indicating not much sensitivity with respect to AMOC strength, but sensitivity to AMOC depth, similar to the C13 data. Also indicating these simulations here around 2,300 meters are all similarly consistent with the sediment data. Again, AMOC strength is not very well constrained by these. So very consistent results for radiocarbon and for C13, so this indicates some robustness of the results. In order to understand a little bit better the radiocarbon results, Juan has plotted here the Southern Ocean reservoir ages on the vertical axis as a function of AMOC strength in the top left and as a function of AMOC depth on the lower left. And you can see in the Southern Ocean reservoir age is not very strongly dependent on AMOC strength. So there's a lot of scatter here in these data, but it is very strongly related to AMOC depth. So indicating that AMOC depth strongly controls Southern Ocean reservoir ages, which then are propagated into the interior, and they affect whole ocean radiocarbon age, which is shown here again in this graph and this two-dimensional AMOC depth, AMOC strength phase space, indicating that the whole ocean radiocarbon age is determined by the Southern Ocean reservoir age. Okay, so we can look a little bit more into the effects of AMOC strengthening and AMOC deepening on the isotope distributions, and that is shown here. So in the upper series of panels indicated by the green frame around it, those show the effects of AMOC strengthening. So a simulation with a 21 Sverdrup overturning, a strong, minus an intermediate of about 15 Sverdrup, and both of these simulations have a very similar depth of 3.1 kilometers. So if we just look at C13 on the left first, we can see very small effects of the AMOC strengthening on C13 distributions. So in the deep ocean we see a maximum of 0.2 per mil increase in C13 in the South Atlantic, but mostly the changes are smaller than 0.2 per mil in most of the rest of the ocean. Similar for radiocarbon age, the radiocarbon age decreases a little bit in the southern South Atlantic and in the Indo-Pacific Ocean by about 100 radiocarbon years. But again, this is a very small change, particularly compared with the lower graphs here, which show the effect of an AMOC deepening. So here you can see in the deep North Atlantic, the AMOC deepening leads to a C13 increase of more than 1.2 per mil, and a radiocarbon age decrease of more than 700 C14 years. So much larger effects of AMOC deepening compared to AMOC strengthening, and this is really what explains why the model data misfits are much less sensitive to AMOC strengthening, to AMOC strength compared to AMOC depth. Okay, to wrap up, I've showed that carbon isotopes provide strong constraints on AMOC depth, but not on AMOC strength. And this kind of raises the question or the need for other proxy systems, and we're currently looking into protactinium thorium and neodymium isotopes, which perhaps provide stronger constraints on these overturning rates. So from this model data comparison, we conclude the AMOC depth was about between 2 and 2.5 kilometers during the last glacial maximum, and that is about 500 to 1,000 meters shallower than today. So this is a very robust result. The AMOC strength, however, could vary between 8 and 17 Sverdrups, so all of these simulations are similarly consistent with the data. And finally, I would like to mention that our results are consistent with the recently published paper by Gu et al., who used CESM simulations, although they only had 3 simulations and we have many more, so we could fill out that phase space much better than they could. But the results are very similar. So thank you very much for your attention, and have a good rest of your meeting. Bye.